people love neural networks because they seem to be like the brain. And they kind of are. It's kind of interesting. But is that what you need? I mean, it's very interesting to look at academically, but is that what you need if you just want to predict some sales?
Hi, Jared. Welcome to the Data Scientist Show. Jared is the CTO of Brainome, a company that builds a data compiler product that takes tabulated data, builds and trains from the ground up self-contained Python predictors that can be run as standalone or imported as library in the production environment. No need for APIs or complicated ML ops. Brainome can be installed via Docker or pip install and can run on user's machine or in the cloud. He's also an adjunct professor at UC Berkeley. He teaches experimental design for machine learning, computational structures for data science. Welcome to our show, Jared.
Hi, thanks, Deliana. Thanks for having me.
Yeah, so you started your career studying computer science. How did you transition into getting to machine learning?
Yeah, and so in my case, that is actually happened pretty early because I actually just was interested in artificial intelligence. And back then, the definition of artificial intelligence was the stuff that computer science can't do yet. And well, it sounded exciting because it's, the stuff you can't do yet is what I wanted to do, like science, basically. And so I started doing machine learning and backpropagation and neural networks basically in 2001. Yeah, basically haven't left the field since then.
Oh, wow. So if someone is studying computer science, but not specifically focusing on machine learning and AI, do you have any advice of what is the best way for them to transition into machine learning?
So it's interesting because let me first of all say the ways that people do transition and then the ways I think people should transition, because I think there's a disconnect. The way people do transition usually is they know how to program, they know how to use APIs. So somebody tells them, hey, use scikit-learn or use one of these open source or commercial APIs and just do it. And as they do it, then they encounter into some questions and some problems. And of course, what they do is they use Google and find the answer on Stack Overflow or find the answer wherever it can be found. And slowly they're getting into the field and they're getting some experience with some data types. And as they get more experience with data types, they think they're the expert on that data type. And that's how it works. That's one way. Another way is quite naturally what happened to many fields of computer science, for example, including my own with the multimedia field. And most of my research was in my contributions in sort of papers was in the field of multimedia computing, where it was in the beginning, in the early time, it was all about encoding multimedia in a way that it can be transferred over different, sparse channels like, internet that isn't very fast. Obviously that's solved. The very fact that we have a video podcast right now makes that clear. And that we do Zoom all the time now during the pandemic makes that clear. And then the field pretty much at the time when I started doing machine learning, transitioned into a machine learning field about finding videos based on their content and so on and so forth. So many computer scientists also got forced into machine learning based on their field. And that often was a little sticker shock because now, instead of the traditional knowledge that you have in operating systems and compilers and so on, it becomes knowledge about statistics and covariance matrices, Gaussian mixture models, and so on. So that's how this happens, I think, on the two levels. And the first level more like right now with young people, and the second level more like with more senior people. Now, how we should transition into machine learning is actually, that's interesting. I think, first of all, most people would say take a statistics class. And I think that's not wrong. But I also think, and that's what I'm developing sort of at UC Berkeley, is to create a class that actually tailors the computer science knowledge that we have. For example, the building of computers itself, right? It's sort of a meta math activity where,
right.
you know, how do you build a CPU that adds two numbers together and so forth and so forth. Yeah, guess what? If you see a neural network as a circuit, you will find out that you're actually also just building a computer there, right? It's just a different kind of computer with different components. So the component is a neuron and not a transistor, and so on and so forth. And as we use that knowledge, we'll actually be more efficient also with sort of the machine learning approaches and the AI approaches. Now, while that's going on, I think another thing to take, as you know, if you want to do something right now, obviously taking my class would be self-advertisement, but obviously I recommend that. But
okay.
if you
sorry, so for people who are not a student in Berkeley, can they take your class?
Yes, I can. We can make the link available. It's all on video anyway, so that's totally
great.
fine. Yeah. So it's all.
I'll link it in the notes.
Yeah, I can send you the link. What I was also gonna say is take a physics class. And why would you take a physics class? Well, especially statistical mechanics and thermodynamics, you will see that lots of the knowledge that we should actually have to create models is already there. It's just encoded into a different language, into the language of physics. And it turns out that you know, lots of the physicists have solved problems that we're still working on in machine learning many not just decades, but some of them actually centuries ago.
Oh, wow. For example?
Well, here's the funny thing. Think about it. The first data scientist for me was actually Isaac Newton. What did Isaac Newton do? Well, apple fell on his head, goes the legend, right? So what do you do with the apple? Well, you find out, okay, why does it fall on my head? Well, the first thing you do is you ask yourself, okay, what happens if I vary the height of the apple? What happens if I vary the size of the apple, right? And what comes out is, you know, E equals mgh is a formula. But the first thing he did was create a table of different heights and of different sizes or masses of the apple before he came out with the basically linear correlation here of E equals mgh. And this is the interesting part. That is data science, because it doesn't matter if your numbers are describing an apple is falling or if the numbers are describing something else. Ultimately, that's data science. Now, what's new compared to physics from 500 years ago, and even compared to physics from 50 years ago, is that we are automatizing this process. So instead of a physicist building that model, it's a neural network from Google building that model, right? And that's actually kind of a little bit of a problem, because the physicist also made this model such that he can explain it to other people,
right?
And it's reproducible. That there are certain standards in these models that we actually haven't adopted yet for machine learning model. Having said that, that should be the goal, that all the machine learning models become explainable, repeatable, reproducible, all of these things, because otherwise, obviously, these models aren't useful in science, to be frank.
Yeah. Do you worry that with a lot of data available, people are kind of going to be lazy and actually try to derive the theory to explain an effect in physics or some other domains?
And that's totally fine as long as you can explain it, right? So I think there's a whole field of scientific machine learning where the trick basically is, can we make the model building in such a way that you know, a differential equation comes out or something, right? So that it looks like the science that we know of. Now, I also have a comment on that. The first one is, the most important thing that we're currently as machine learners not obeying is Occam's razor. Okay, so there's, you know, big companies saying, oh, we have this 100 million parameter model and it's so powerful.
Right.
Like, I'm not impressed by that. But I would be impressed if it was a 100 parameter model and it was to be so powerful.
Right.
Okay, because the point is that makes it general. We don't know how much this model overfit / memorized whatever it was put in. We have no clue. So what we do know is that something like every fundamental physics equation is mostly linear or maybe quadratic, right? And if you look at Newton, E equals mgh, right? I mean, it's as simple as it gets, right?
Yeah.
Or 1/2 mv squared. Come on, right? And I think the ingenuity also of Einstein's formula, E equals mc squared. Come on, how much more simple can you get?
Right.
they're not the long, I mean, obviously we know if you derive it, then there's a Taylor approximation. It's actually much longer than that, and so on and so forth. But that's the whole point. You want to create knowledge usually is short and concise. And then if you detail, obviously things can be a little longer. But the reality is that we're not even aiming for that in machine learning right now. We are aiming bigger is better. And this comes from the fact that I think, well, frankly speaking, people want to sell hardware and compute because Moore's law ended. We cannot just make the frequency of the CPU higher to accelerate computing. No, we have to sell more cores, and now we have to find applications that are easily parallelizable. And machine learning seems to be one of them. So let's have people do machine learning forever, in a never-ended fashion, and with more and more neurons and more parameters, so that we can sell more and more compute power. The reality is, if we want machine learning to integrate with the scientific process and to give us any insight that makes sense, we need to actually go the opposite direction.
Yeah, that's a really great insight. So what I always advise people is if you can solve a problem with logistic regression, then there's no need to build a complex neural network, right?
That's the same thing.
Yeah.
And so this is very interesting because there's a lot of ideology in there. People love neural networks because they seem to be like the brain. And they kind of are. It's kind of interesting. But is that what you need? I mean, it's very interesting to look at academically, but is that what you need if you just want to predict some sales? Not necessarily, right? And it turns out in practice, stuff like random forest and XGBoost is actually in practice often beating these algorithms. And it took, the connectionist field a long time to actually come up with deep learning and to finally find an application for where it's useful. And of course, I will tell you that I have a publication out that shows that these deep layers are nothing else but obviously a convolution to get rid of a lot of the noise that is in images that could easily be substituted, for example, with JPEG or other compression algorithms that we already know. And guess what? The whole thing would be a lot faster. Yeah. But I appreciate the idea that, hey, we have a set of neurons and it just does it. I mean, that is kind of miraculous, but it's not necessarily what everybody needs when they do machine learning in practice.
So you previously talked about overfitting. I think that's generally created a lot of problems for machine learning practitioners. So can you talk about how in practice can we reduce overfitting? How do we avoid it?
Well, the first thing is to understand overfitting. What does overfitting actually mean? And obviously overfitting has to do with a number of parameters. And so the way I saw it in the class, and also the way the Brainome tool implements it, is that we say, well, first of all, we need a standardized measurement. What each parameter in a machine learning model means is different based on the machine learner. But we adopt the information theory ideas from David McKay. David McKay in 2003 published a book. He actually just published two. One is a popular book on energy, and the other one is a very mathematical book. And really, just chapter 40 is so deep, even though it's only 6 pages, that it took me, basically a bunch of years to understand it fully. Yeah. But it's really interesting because it really explains a lot. So overfitting has a couple of problems. First of all, we should use information to understand overfitting. So how do we do this? First of all, think about this. You have a table. Let's call it a classification problem, and let's call it binary classification. Let's make it all easy for now, okay? And even more easy, let's make it a balanced classification problem. So it could be sick, not sick, has COVID, has not COVID, or cat, dog, or whatever. It's balanced binary problem. You have 100 classes that are not sick and 100 classes that are sick, okay? What we do know is that the probability, knowing nothing about how the input relates to the output, and the input could be anything. It could be, age and weight and, fever and symptoms, or whatever, okay? And then you want to find out, is it sick or not sick, okay? The question is, not knowing anything, and trust me, this single neuron doesn't know anything. What we can say, however, is if there's a balanced binary outcome, that the information I gain whenever I know the mapping between the input and the output is 1 bit, okay? So now I have a measure of information. Every time I predict a balanced binary class right, I have 1 bit of information. Now that's interesting because now we can say, well, guess what? If we created a machine learner that took this table and just overfit it or memorized it, how many bits would we need? And at first approximation, we'll see later on, this is unfortunately not completely true because of the curse of dimensionality. But for now, once you have small number of dimension, yes, if you had 10 bits of outcomes, or in our example, we started set 100 and 100, so 200 bits of outcomes, you would need 200 bits, well, of memory to memorize those outcomes, or you would need how I call it, 200 bits of memory equivalent capacity in a machine learner. Okay, and now that gives you a measure. That means if your memory equivalent capacity of a machine learner is larger than 200 bits, you might still not overfit. But as an engineer, I'd say you'd overfit. You used more or equal the amount of bits you needed to memorize the table. So you're overfitting. So as an engineer, I want to guarantee you're not overfitting. So you need to use less than that, because that's the only way you derived something smarter than just memorizing the table. And so now comes the big question, okay, but how do I know the memory equivalent capacity of a neural network or a random forest or decision tree? Well, there's some papers that we should probably link that explain how to do this for neural networks. But I give you a quick example about a decision tree. It's pretty simple. If it's a balanced binary tree, right, each branch is 1 bit, right? So every time you say yes, no is 1 bit. So in general, it's the log of the leaves. So you have your memory equivalent capacity for that. And now that is not even a new notion. I mean, I kind of coined the term memory equivalent capacity, but the reality is that Shannon, there's a thing called a Shannon number. And Shannon already asked himself, what's the number of decision tree branches and leaves that I need to solve chess? And if you calculate that base 2, you figure out it's about 400 bits. And that's actually extremely interesting. This is basically a chess algorithm in the ideal could fit into 400 bits. Now, what happens in practice is it takes a little more, but really not that much more. If you ask yourself, a lot of very, very early computers already had chess implemented on, you know, like even like a Commodore 16 or something. And even earlier than that, we had chess implemented in very little RAM. And it turns out, yeah, because 400 bits is not that much. And then I can tell you that if you did it in a neural network, and people have done this, their neural networks are obviously a lot larger than the 400 bits. So yeah, we should go back to this point where we actually figure out how difficult is a problem and how to do that. And again, for chess, for example, overfitting is fine because in chess, once you have all moves, there's nothing you need to generalize. But if you have input that you can't predict is going to come in, then you need to have sort of your tree handle different stuff it hasn't seen. And for that to happen, you have to have, it's basically, as an engineer, you would say your memory equivalent capacity needs to be a lot smaller than if you just memorized. And people may ask, and I just add this because really I would need a whiteboard to explain this a little better. Let's do this. So you do this. You have a table, again, 100 patients say sick and 100 patients are not sick. And you just basically create a finite state machine for that table. Well, the easiest way to create that finite state machine is to have each input and an arrow to the output. The next row of input, arrow to the next row of output, and so on. So for 200 rows, you create 200 arrows. And what does it give you? A lookup table, right? A dictionary. Exactly, if you see that input again, you know what the output is. But what if you vary the input just by a little bit? Yeah, you have a problem, error, right? I don't know what to do. Now let's find the opposite. The opposite is we take the same table and we do one arrow, only one arrow. The arrow goes to the majority class. So basically we say, let's say it's a 60-40 problem in this case. And we say 60% it's yes, 40% no. We always say yes. Yeah, perfect. We get the best guess. And we can handle any input. Perfect generalization, but no accuracy. So that by itself tells you, okay, the truth is anywhere between 200 arrows and one arrow. It's anywhere in between. So we want to find the point where we have the highest accuracy with a highest generalization, which is the least amount of errors that give you the highest accuracy. And again, that's nothing else but saying, because each error is 1 bit, remember? You want a memory equivalent capacity that is small. So we still memorize everything, but in reality, we also generalize so that when the test set comes, we have a higher chance of making that right. And now only comes the work of saying, okay, what's the memory? What's the finite state machine implied by this neural network? What's the finite state machine implied by this random forest? Well, that's a little bit more work, but that's the work we've done in Brainome so that we can actually make this actionable. And basically, we end up building a compiler that just takes your data in and puts a predictor out with a model built using, this theory.
So for data science practitioners, how can they use Brainome to use this data compiler functionality to get results that's not overfitting?
Yeah, so the easiest way is to do pip install Brainome. Literally, it's just a pip install, and then you get a demo version. And you can already do most of the stuff with it. We are mostly right now focusing on sort of large data and also large number of attributes. Because as I said to you earlier, that once you actually, all of this, what I just told you is true for small number of attributes. For a large number of attributes, things change a little bit, and then you have to sort of derive curves on how things change. But all of this we have done. And for example, for genomics, that's really useful. Genomics, you have 21,000 columns, like all the genes, and then 500 patients. How do you get anything out of that? Yeah. Well, with the right information measure and sort of correcting for this problem, you can. And so that's why our sort of customers, enterprise customers, are in that realm mostly, so the biology and genomics, because we are really, really quick. Within 5 minutes, we find cancer genes, and we've done a study on 33 cancers on the Atlas and on the Cancer Atlas. We just download the data, do it, boom, 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 boom. Right now, people are still tuning and don't know whether they need to set their parameters, because not only are they fighting with their machine learner to be correct, but also they're fighting against the curse of dimensionality, which again, once you measure it, is not a problem anymore.
That's awesome if you can do that within 5 minutes. So how, what's the technology in Brainome that enable this type of speed?
Yeah, and so the interesting part here is the technology is measurements. Okay, when people, I think we have a big lack of philosophy in machine learning, and we often forget when we deal with all these numbers that's not how engineers do it. Okay, if you want to engineer something, and engineers are extremely successful in doing things, like they build cars, they build bridges, they build houses. Well, but every engineering starts with measurement. we first draw the house and then we build it. We measure the speeds that we want to achieve and the forces, and maybe we simulate a little bit the aerodynamics of the car before we build it. In machine learning, we just build something and hope it works. And what happens here, if you do that, it becomes like guessing and checking. It turns out the Vikings, when they were building a new boat, they built 10 of them, and then one worked, and then they copied the exact format of the boat for the next boats. That's what we do here too. AlexNet worked really well, on this one competition benchmark. So now everybody's using AlexNet for computer vision. Well, that's like the Vikings. In reality, we should be starting to measure and figure out how things behave. And that's basically the trick that Brainome uses. We know how things behave. We don't know it perfectly, but we know it better than nothing. And the trick is that measurements just means you don't have to guess. You just follow the measurements, and guessing and checking takes forever, but measuring and then doing something does not. And that's the whole trick. The trick is not an extra CPU. The trick is not, more memory or any of this. The trick is really just, let's be intelligent. Let's do engineering.
Yeah, use first principle instead of getting lucky and see whatever works. Yeah.
Yes, that's putting it even more brutally than I do. Yes.
So how is Brainome different from AutoML in this sense?
Right. So AutoML in general is just guessing and checking. I mean, they use a lot of compute and they try every model that they have and just see if it works. Brainome, the first thing it'll do, it'll take your data and it measures. The first thing it measures is it actually enough data for an ideal machine learner to even learn something? Because if an ideal machine learner doesn't learn anything, you don't even have to start to do anything. You need to collect more data or you have to do something with your pre-processing, right? Once we figured out, yeah, there's probably enough data to do something, we figure out which of the 3 machine learner that we currently support, which is decision tree, neural networks, and random forest, would be the best for it. Based on, well, if we memorize the training data, let's see how few parameters we can get away. We take the one that uses the fewest parameters. And as we do that, we have a model choice algorithm. And again, we need to use memory equivalent capacity and not just parameters, but just as an overview. And then we build it. So how do we build it? Well, we build a neural network, for example, neuron by neuron by neuron, boosting it neuron by neuron by neuron, or a random forest, same is boosted. And people have found out that boosting is great. But still, most of the boosting that's done is completely random. Just put another tree in and hope, let's see what happens. Instead, we know we probably need 3 more trees or we need 3 more neurons. And then we see if after 3 more neurons it didn't work, what's going on there, right? So once you have an idea of where you want to go, it's much easier to get closer to a global minimum of your error than if you don't have an idea. And that's how it works. And we put this all we package this all nicely up into a command line tool, which again can be installed with pip install Brainome. And we have a pre-processing with it that, so for example, Titanic, you can just take that file, even though it has strings and it has floating point numbers and integer numbers, all of this mixed, fine. Just take the file. We'll do a pre-processing that will basically convert everything into numbers, but preserve the information content of each row and column. That's the whole point. And then do our measurements, choose the model, build the model, and out comes a predictor in Python that you can just use. And the nice thing is put that on your GitHub with your paper, and you have a completely repeatable, reproducible thing because this predictor is self-contained, and you don't have to worry about, okay, how do I export my model and make it so that other people can use it? What if the library version changes? All of these kind of things we solve because we don't want to, we want to make things reproducible, repeatable, and transparent.
Mm-hmm. Yeah. So is it correct to say this is not a model-focused approach, it's a data-centric approach?
Yeah, it's a data measurement of the data-centric approach. Yes. Mm-hmm. So we try to cut on the ideology, that's usually behind, oh, we need to use deep learning, oh, we need to use random forest.
Right.
We try to make it objective.
Right. So a lot of data scientists have the challenge that we build a model, it's using one type of framework, for example, random forest, and then the data changed and then the model doesn't work. But if the model is already in production, what we have to do is try to figure out ways to improve this random forest model, right? But it will be very hard for us to change into another framework. So with Brainome, you don't really have this fixed framework when you deploy. So whenever you have a new data based on this information measurement, you can generate a new model to solve the problem.
Yeah, and the information measurements are extremely useful for situations like you described, which we call data drift. Mm-hmm. Because, and this is an easy example to think about. If you think about a Gaussian, right, it has a mean and a variance.
Yeah.
So if your data drifts, one of the two will change. But for us, we measure memory equivalent capacity. That means we would measure how much does it take to store that Gaussian in both the variance and the mean. Mm-hmm. Well, guess what? If any of the two changes, then the storage requirement will change. I mean, it would be extremely, obviously now people could say, wait a minute, but what if it just changes the variance just in the right amount and the mean just in the right amount that you don't see a change? Mm-hmm. Okay, I give you this point, but good luck. In real world data, you would see the change, okay?
Yeah.
And that's exactly how we do it, because the point is you see, wait a minute, I measure the new incoming data and based on, for example, some just sample labeling you have to do, and you see, oh, wait a minute, the memory equivalent capacity changed drastically, then you should absolutely not anymore trust your models to do the right predictions. In fact, you should go and retrain.
Mm-hmm. And so who should use Brainome? You mentioned you can just use pip install. Is it mostly built for engineers, data scientists, or so for example, if someone don't have a technical background, can they use it?
So the way I think about it is like as a quick snap camera. And I also always say your photographer will not be very happy about a quick snap camera, right? So quick snap camera does, or in the end, the camera we have on our mobile phones is, it enables everybody to do some photos quickly. But would you do this for your wedding? Probably not. So there's still a photographer you would hire for that, right?
Yeah.
So what that means is, if you're a data scientist, or you have data scientists, use them for the interesting, very challenging problems, for the more advanced stuff like wedding photography, like so the equivalent of this. But our tool sort of makes it easy to build models, even for people who don't have any data science background. But yes, it's kind of like the quick snap. You'll get one photo and then you got to live with that. And then people will say, yeah, but you could do this and this and this. Sure. But do you want a photo or do you want to hire a photographer, right? And so you just have to make this distinction. And then on that note, I think, and we know this from sales calls, obviously, people, there are basically three kinds of ways that we are appreciated. One way is exactly that. Data scientists are extremely rare commodity right now. And if an institution has like 2 or 3 data scientists, it would be great if some of the less challenging work could be done by not data scientists, and to just, run the tool and done, right? That's number one. Number two is, we deal with the curse of dimensionality much better than I would say any other tool, because we measure. And so we are in talks a lot with genomics and sort of with people who have high dimensional data. So they should definitely approach us and try us out. Mm-hmm. And that could be even data scientists, because frankly, the only way to deal with high dimensional data is to measure it. The third part is that we are also thinking a lot of what we do, the measurements itself could be useful, but that kind of requires a little bit of knowledge, right? And I think that's going to be very interesting to drive like an engine that's already existing, so improving AutoML algorithms that already exist, but instead of them guessing through all the models,
right, we
will just basically tell you which one is the best, and then go from there. And I think especially for like very new stuff, like when we think quantum computing, right? Quantum computing, the number of bits is limited, the qubits that they have is limited. So what happens here is that they can't just use 100 million parameters. They need to use really small models, and also known if the problem is even solvable with a small model. So that's where we come in.
Mm-hmm. Yeah, I can see also it's useful when, like you mentioned, I have a lot of data. Sometimes data science team or the business don't know whether it's worth it to invest time to develop a project. So instead of having data scientists to do exploratory analysis, build a model, you can quickly use Brainome to run a baseline to see.
Exactly. Yeah. Yes, that's exactly right too.
So yeah, I think that would be very useful for a lot of new research, and also save data scientists a lot of time. So you mentioned the type of measurement you do. So for data science who want to understand more about how to do this type of measurement, what type of books or courses that they can take to learn more about this?
Yeah, I mean, as I said, so the original idea is best described. I think the original idea is Thomas Cover in the 1960s, but I wouldn't recommend to read that, because it was ingenious, but it's not necessarily the most pedagogic approach. David McKay is the book to read. 2003, Information Theory, Learning Algorithms, and Information Theory, Inference, and Learning Algorithms is the book. And the chapter 40 there is dense, but it's basically describing everything I just said for a single neuron. Mm-hmm. And of course, Brainome extended that from a single neuron to different machine learners, and also from just binary classification to multi-class classification, right? And actually doing it, not just describing it. It is interesting how this book is actually really using information theory to unify a couple of fields. And it's a known book in certain communities, but it should be probably wider known. So I'm doing that here right now.
Yeah.
Right.
Yeah, that's what I noticed. I feel when I look at a lot of modern data science program, we don't really learn information theory. Do you feel this something that's missing in a lot of curriculum?
Absolutely. I think information theory got boiled down to the super special field of communication between two endpoints, which is where it came from. Shannon invented it as a theory of communication. And of course, the Wi-Fi area is big, so that even doesn't make it smaller, but it's still bigger than that. And I would say, and this is now my personal opinion, here's what's interesting. Apple says there's an app for everything, right? That's actually very interesting if you think about that sentence scientifically. Because what is an app in the scientific sense? An app is a model, right? It models some task for you. It helps you do something. And if there's an app for everything, that means actually kind of there's a model for everything. And that means, and this struck me when I saw that, for example, the entropy, the notion of entropy exists in chemistry, in biology, in physics, and in computer science, which is a second indicator that actually information theory is kind of the universal theory that many people have been looking for. And now information theory doesn't solve it all. It's not that, but it helps you to model and to understand models. And for me, sort of a memory equivalent capacity is as indicative as, let's say, a differential equation, right? A differential equation just tells you how something changes. It doesn't actually tell you the actual thing. And a memory equivalent capacity doesn't actually tell you the real model, but it does tell you the size of it, which is not nothing. And so it's kind of sort of this sort of indirect math that has been used by modeling for modeling by the physicists for a long, long, long time. And I think we need to start doing that in computer science. And in computer science, we don't deal with differential equations and calculus. We deal with information, bits turning on and off. So information theory would be the thing for us to learn. Also linear algebra, but I don't think linear algebra is undertaught, while information theory, I think, is very undertaught.
Right. So for students who are still in school, besides you mentioned earlier physics or information theory, are there some other course you wish more people take? Yeah,
I want to be also specific. I think physics, take statistical mechanics is like the one thing that's super, super close. And especially you will understand information theory. If you take statistical mechanics first and then information theory, that'll probably help a lot. And the other one is thermodynamics, even though I think the way thermodynamics understood right now is less in the information sense than it should be, but it may be worth taking a look. And it absolutely is useful to take discrete math classes and really think about probabilities in a discrete way. And also graphs and all of these things are useful.
Yeah.
But in terms of sort of the core, I think information theory and statistical mechanics are the two ones that I would say I would even start teaching. If I could change the curriculum, I would start teaching them in computer science because they're actually the science behind computing. While what we do in computer science often is just the engineering of how to build programs.
Yeah, cool. And then you teach students in grad school. I remember when I was in grad school, I struggled to find a motivation because sometimes I find it difficult to find field related to those theories. I don't know how I'm going to use it in the future when I have a job. So for students who feel lost in grad school, what kind of advice do you have for them?
Yeah, and this is this is kind of this thing is, what would you teach your former self if you could go back? Okay.
Right.
And I would teach my former self the following. I completely understand that once I had to go through the horror of high school, the horror of SAT, the horror, all of these horrors, that you finally ache to learn something you can actually use to make money. Okay, I totally get it. You want to be independent, have your own apartment, your own car, and all of this makes total sense. And I 100%, I'm with you on that. But if you think about your university education as an investment, both in time and also in the US, especially in money too, you want to invest into something that lasts you a lifetime. Okay, because neither your apartment nor your car, and well, probably also not your coffee, will last a lifetime, unfortunately. But the point is, reality, you want to shape your brain in a way that is generalizable to all the life situations you will encounter in your career. And guess what? The fundamentals are those. They never change. Shannon's information theory will never change. It's applicable as is. It will be extended. We will understand it better, all of this. And you will understand it better as the years go by and you apply it. But the trick is that the best thing you can do is to just be patient, take the time to learn those fundamentals, as you will see that it accelerates your learning on the job and your learning later on greatly. And it's a typical college professor thing to say, I know, but it's also my own experience. And I was the same way. I'm like, just give me something I can apply and then build the next app, make money, and I'm good. Yes. But after that, what's the next thing? And often what happens is that people in their midlife come back and say, actually, now that I have done all these practical things, that makes total sense what they said in college. And then they come back and do a grad degree. And that's okay too, by the way. It's not wrong at all. But while you're at it already, just take the time and learn the fundamentals, because they are really, really the thing that generalizes to the rest of your life.
Mm-hmm. Yeah, I really wish someone can give me this talk when I was in grad school.
Well, we can do it in the podcast now. And actually, the other advice that I can give is it's not too late. Let's say you just finished grad school and I was like, damn it, you can totally keep learning. So you finish grad school in computer science and you hear this podcast and you think, hey, he's right, I should have done statistical mechanics and information theory. Well, guess what? There's YouTube, right? So for example, Leonard Susskind's lectures from Stanford on statistical mechanics are extremely good. They're actually tailored to computer scientists because he's teaching in the Silicon Valley and people ask him about 0 and 1 all the time. It makes sense, right? But you can go on YouTube and you find the good lectures and you just take them. And there's nothing wrong with that. And I even say this as, you know, as a professor myself, because often you think like, oh, this infallible person. No. The point is, the difference between, you know, sort of us and the rest of the world is we just like to learn. Right. And I will not stop learning. I will keep doing classes. And the funny thing is that more and more, the older I get, unfortunately, the more I like to take fundamental classes, because more and more I learn that, oh my God, if I had known this before, all the explanations would have been so much easier. And also the explanations that I need to give now to my students become so much easier, knowing, you know, the physical fundamentals of what computing is. Because after all your Python and Ruby on Rails and whatever you do, in the end, you're just flipping bits, you know, and it's really depressing sometimes to think about your PhD in computer science. And I can say it's because I have one. Yeah. My PhD in computer science is really just a degree on how to flip bits, how to turn switches on and off. Yeah. And yeah, it's complicated, I guess, but that's all we do.
So that's great advice. Thanks for that. And when you are doing research or when you are working on project on Brainome, we know a lot of times research fail, or especially when you are working on some innovative approach. So how do you, if for example, you have a deadline and something is not working, how do you handle that type of stress?
Well, I think the first thing is to actually take a step back and realize that if you couldn't be failing, it wouldn't be research, okay? Research is defined by the fact that you don't know what you're doing. And by the way, another word of encouragement, if you're more on the theory side and people tell you you're talking garbage, yes, because before theory is sound and complete and perfect and works, it's garbage, okay? It's normal, okay? Because the experiments will fail, otherwise you wouldn't have to do the experiments. And your theory will not make any sense, otherwise you would need the theory, okay? So once the theory makes sense, obviously everybody, people will understand it and like it. But before that, it takes a while to develop, just like the experiments. Both of these need to be able to fail. They just look differently when they fail.
Yeah. That's very powerful. So now let's go back to talk a little bit about yourself, your life. So when you were a teenager, when you were a kid, or were you always interested in computer science? Like, what were you like when you were a teenager?
Yeah, I would like to give you the underdog story where everything changed. But I don't have that. What really happened is that there was a computer in my basement when I was 7, and I was so fascinated. When I was so fascinated with it, was a Commodore 16 actually, as a sort of a sister to the Commodore 64, which most people know, but it was mostly used for gaming. The Commodore 16 by then had my way better BASIC, and there weren't a lot of games. What was interesting about it is that the BASIC was good, as I said, and so there were some books out on the table with the computer, and my dad told me, if you type in that stuff in cursive, things will happen. And you can't imagine the adrenaline that a 7-year-old gets when you type something in that you completely don't understand. Because first of all, I was growing up in Germany, so English was not my language. And I was 7, so reading and writing is, I took probably 30 seconds to say print to find all these keys. So print meant nothing to me. Of course, it means print, but for me, it meant nothing. And so I type in the cursive lines, and stuff happened on the computer. That was the biggest, coolest thing on earth. No, I didn't know how to save. Saving was on the cassette decks, so it was not real. So instead of doing that, I typed it in again. But here's what happens. You make mistakes, and then something else happens. And of course, the investigative me started to figure out, okay, what do I have to change? What did I do wrong? Such that things change. And so I taught myself programming. Basically, if I was a Chinese programming language or something like that, as a Westerner, you would have no chance of seeing what this is. But this is how it was for me. It was English, which I learned 5 years later. And so I learned just by trial and error to the basic programming language. And I'm not saying trial and error is bad, but obviously everybody would agree that I could have been, if somebody just taught me, it would have been much faster, right? And in the same sense for machine learning models, by the way, if somebody just guides you with measurement, it's much faster. But the trick here was that I taught myself to guessing and checking computing at a time when it was kind of not yet cool. And then through my high school, computing came up to be like the PC became big and so on and so forth. And then lots of people just hired me can you teach me how to do word processing? Wow. Kind of funny because it was just learning the keyboard, to be frank. And the fact that you don't type and then use Tipex, but you actually can use the cursor keys. And these kind of things were essential that were not there for people that were forced to use a computer. And then I had my first company when I was 18. Wow. To do audio live transmission over the internet, which is kind of funny now because people are going to listen to a podcast right now. And of course, that's nothing. But in 1996, no, I'm dating myself. In 1996, that was something. And so I, however, had no idea about business. So what I did is I put the software onto a machine and onto different machines and rented the machines out. Not a scalable business model, so that failed after a while, but it made enough money for, my driver's license and my first car and so on. It was fun. Yeah. And unfortunately, because most of these gigs were like theaters and sort of open radio stations that was transmitted to the internet, it was all at night. And so I had to excuse myself from school all the time. And my one of the teachers came to me and said, why are you excusing? Your grades are okay, no matter, whatever, but tell me what is going on? You're not sick all the time. That's not right. And I said, no, I'm not sick. I have my own company. I want to do these gigs. And he goes, wait, you built a program that can transmit audio on the internet? That's so cool. I'm like, okay, yeah, I know. That's why I make money with it. And he goes, no, you should participate in what's called Jugendforscht in Germany, which is the Young Scientist Contest. And so I participated and I went to the regionals, I went to the state one, and then I participated in nationals. Didn't win that one, but it was really an experience. And for the first time, I figured out, hey, it's not all about making money. Right. It's actually kind of cool to talk to other people who think about this conceptually. And I have to say that the scientist contest really made me go the academic route because I felt really sort of, oh my God, finally I have people I can talk about this. And you learn so much when you have interaction with people who understand the same things as you do and want to push it further. Yeah. Because until that point, I just was completely self-taught.
Yeah. Wow, that's a very interesting stories. So who are you? What do you do when you're not working on computers, or computers is already like a game for you?
Well, well, first of all, I'm a dad of a 10-year-old daughter. And then also, I'm a scuba diver. I really like nature and to just basically dive down and relax, and no phone is ringing down there.
Yeah.
But in general, I'm just a maker and tinkerer. So I actually enjoy building electronics as much as I build software, and I always did. And also just enjoy, working on my home and stuff, because I just like to. There's some things about physical work that you don't get when you just type on a computer.
Right. So have you ever get inspired by scuba diving or fixing things at home, or, hang out with your daughter in your research?
Yes. So that's very important, actually. I mean, you asked for advice earlier. That's another advice. Ideas don't come when you want them to come. Okay.
It comes in showers.
Anyway, in the shower, or I run. All right. So I'm a runner. And so you run, especially running is really good. Gives you a lot of oxygen in your brain. But also scuba diving, or it comes out of a dialogue with the person you just meet, or something like this. It comes out of random occasions. And I'm known to, my daughter still makes fun of me, I'm known to take to do math in the shower, right? So I would use the fork that came over the shower, the glass, and then use math in there. And so my daughter makes fun for me, but that's okay. It happens when it happens. And if you're really stressed out over a deadline, I think that, as I said earlier, the best thing is to just take some pressure off. It's really the best thing. Go out, take a run.
That's very interesting. And that's what I do too. Actually, before the recording, I went for a run
Good.
to get more energy. Yeah. So what do you think is the future of machine learning and the data scientists who do machine learning, say after 5-10 years?
Yeah, and I don't think the data. So often I think data scientists fear we're going to replace them, but that's not going to happen. Data science is so much more than just model building. But I think model building will be automatized, just like we started in Brainome, and we will not have to think about hyperparameter tuning or these kind of things anymore. I think what I want the data scientists to do is two things. A, ask the important questions. Every scientific endeavor starts with the right question, right? That's the first thing. And of course, make sure to find the data that potentially gives you the answer to that question. And then obviously put it together, make sure you have enough, or maybe you have to augment it, or you have to find other data, or you have to do some feature extraction. All of these things will still be happening and are the task of a data scientist. But at least the data scientist doesn't have to think about anymore, okay, if I use this scikit-learn model, oh, wow, the default parameters gave me good accuracy, but is that overfitting, or do I have to try other machine learners? Is that the best that could ever be? That gives us sort of an endless open task. That'll hopefully go away.
Yeah. And then you mentioned asking the right questions. I also think that's very important. So do you have any tips for data scientists? How do they ask better questions?
Well, I think that is the ingenuity of the scientists, to ask the right questions. I don't think there are standard tips, except listen and observe. So one thing that I was always, and even early in the beginning of my academic career, I asked all myself, how did Einstein get to where he got? And it's kind of funny, because what he did is he questioned time, right? You go and say, by the way, time is not absolute. And that's something. So often the biggest breakthroughs are right in front of you, and are the things that you think you know. Okay, so all the physicists thought they know what time is. Turns out they didn't. So it's all the things you think you know that are actually beg the questions that are really interesting.
And then basically question all the assumptions, the things you take for granted.
Yes. And of course, that is also important. That's why we try to have diverse teams, because in non-diverse teams, the problem is that there's a cultural background that is a bunch of things that may not just not be true, right? Yeah. So in a diverse team, there's more questioning, the and so on. So that's where all these things come back in. But yes, question your assumptions is absolutely right.
Yeah. And for data scientists or anyone interested in machine learning in general, do you have any favorite books or courses you would recommend? Of course, you want to recommend your own course.
Yeah, I already did that. I already did that. I would say in general, and this sounds weird, all the books and courses that are older are all pretty good. So there's two things I want to say. Number one thing is read the originals. For example, read Rosenblatt's paper about the perceptron. Guess what? He already said, oh, information theory on a perceptron would be super interesting. Yet nobody really followed up with this in mainstream, right? It was mostly Thomas Cover in the 60s and then David McKay and maybe now me and a bunch of other people. But the point is mainstream did not follow up with that recommendation, right? So, but Rosenblatt himself already said it. So first thing is read the originals, read Rosenblatt, read Kolmogorov. Kolmogorov showed that 3 layers of a neural network are enough. So how is that compatible with deep learning? You should ask that, right? Now you get some insight, right? Your assumption is deep learning is awesome, right? But why did Kolmogorov show this? Is Kolmogorov's proof wrong? I can already tell you Kolmogorov's proof is not wrong. He's very, very rarely wrong. Yeah. So there's another explanation for it, but hey, let's question that. So read the originals is my recommendation number one. And recommendation number two is, in general, try to read books, and these are usually the ones that are in the 80s and maybe beginning 2000s, but not much later. Then instead of just presenting you, here's a formula, use that, right? Or here's a black box, use that. Or here's an API, I teach you how to use this API. Go buy the books that go from the fundamentals. For example, I completely recommend go and implement backpropagation. Honestly, people think it's a primordial task. No, it's not. My homework back then in 2001 was to implement backpropagation in a week. Yeah. Totally do that, okay? Now you've understood how that stuff works and it's gonna be demystified, okay? Yeah. So go to the fundamentals and also just implement it yourself. You'll learn the most from that.
Yeah. That's really great advice. I did it myself when I was learning machine learning, and then everybody was complaining, oh, why would you have to do this by hand? It seems so trivial. Right. But then when you actually do it, you're like, oh, I actually don't understand this. It seems simple, but it's not.
Right. And yeah, you see the problems that happen. For example, it doesn't converge. Why doesn't it converge? And then you start to play with learning rate. Yeah. And you see, that's where this problem comes from with the learning rate hyperparameter, and so on and so forth. And really, again, advice number one is read the originals. Advice number two is read the books that were still doing the basic stuff and implement that.
Yeah, that's really great advice. Yeah. And now at Brainome, do you hire data scientists?
Well, so right now we are working on another round of funding, and then we probably will actually hire data scientists, because we mostly obviously we have data scientists, but we mostly have machine learning engineers, and but there's going to be a lot of work about sort of making this directly compatible with, let's say, a genomics format that they all use, like GTEx and so on. And so that's where we need data scientists for, yeah.
And then when you hire a machine learning engineer, what are some the most important quality you're looking for?
Yeah, so the most important quality is two things. Obviously, an appreciation and an understanding of the theory, which of that particular theory that we're using. But the second is to be really pedantic and make the code work and test it, okay? So there seems to be in machine learning a sort of idea that if your model doesn't work, who cares? Or if there's a bug in your model, who cares? It's gonna learn itself anyway. No, that's not how it works, okay? Yeah. So we still have to do rigorous software engineering with all the stuff that we do. And for example, a practice to do that, which is not even, I think, mainstream, is to create synthetic files and make sure you get the result that you want to get, or create uniform random files and make sure you hit the information limits that you should get. And I tell you right now that we tested different machine learning frameworks, including from Google and Amazon. Not all of them hit those limits. They have bugs.
Yeah.
I can't believe these are commercial frameworks. And if you want a personal recommendation, yes, scikit-learn is the most bug-free one. Okay, so on these things, so in general, we want the same rigor that we ask from any other software engineer. And that often seems to be not so clear. And I will tell you that this has nothing to do with the individuals. I mean, first of all, there's a lot of rigorous individuals, okay? But there is, and this is why I criticize this, seems to be in the field a way of let's do it less rigorous. For example, I would criticize NVIDIA for not obeying to floating point standards. We solved IEEE floating point standards, IEEE 754, for a reason, because it was a mess before we had that. And now NVIDIA goes and says, oh, we don't have to adhere to that, we have our own. I mean, that's for me is something that is just not acceptable, just to trade off some cycles to make it a little bit faster. And this kind of stuff is something where I'm saying that's where rigor needs to stay. We have to keep to standards that work and not just, for the sake of 2% more in somewhere, just throw engineering out of the window that is tried and trusted.
Yeah. And what is something you're excited about right now in your career or in life in general?
So a couple of things are exciting in my career, especially the growing demand of taking my experimental design class, which teaches the basics of the theory we are using. So that's really started from a 6 people class a couple of years ago, which is just like a research seminar, to now being way over 50 right now signed up, and a lot of massive engineering students because they know that engineering is important, and that's very exciting for me. The other thing that's exciting is that I finally have with Brainome. I finally have an instantiation, an actual real world program that implements the theory and does useful stuff with it. Because for a long time, it was just all in my head. It's so much nicer to have it in my head. So I'm looking forward for people to use this and for it to be adapted as we slowly rolling it out. Yeah, I think for me, that is sort of it's a big thing in the sense that I have 20 years of a machine learning career, but I think right now I have the chance to shape the field in a way that I think will help the field in a great way. And I'm also asking, I know that I'm not the only person who's thinking about measurements in machine learning.
Yeah.
If other people hear that and agree with me, I'm asking to totally reach out. I think we need to build a community around this, and we need to find out that every engineer is measuring. Why are we measuring in machine learning? It shouldn't just be my statement. I'm pretty sure there's other people who agree. So I'm looking forward to having more discussions in that now.
Yeah, I learned so much from you during our conversation. And for the audience, our listeners, if they want to find you or join this community you mentioned, how can they find you on the internet?
Oh, so yeah. So first of all, we have Brainome AI is our website. And then there's a contact us that's easy. But also I have my own website, which is just my personal website is gerald-friedland.org. And yeah, drop me a mail or drop us a mail on Brainome, and no problem. Or yeah, that's it.
Cool. Are there something else you want to talk to the audience before we wrap up?
No, I think you covered it really nicely. Thank you, Daliana, for inviting me to do this, and I'm really excited for hopefully people coming back trying our tool, and also if you don't like something, tell us. Okay, I mean this is again something that comes from the heart, so we will make it better. And not everything is solved yet. We know that.
Yeah. Great. Thanks again, Gerald, to come to the show. And I'm very excited to see how Brainome will grow in the future.
Yeah, thank you.